So welcome everybody. I'm very happy to be here today with you to present part of the work that we are doing in Adeline Science, which is a French startup and that we are working to help on facilitating the valorization of research data. So today I'm going to be talking about biases in AI, causes, consequences, and potential solutions the way we see it. So as you all know, we have seen the rise of AI and all the promises that it brings, and we see that it can have a great impact in different ways that we treat patients. From precision medicine, we can create new ways of following the patients, we can create digital twins that can help us actually find new therapies. But in order to do this, first we need to find the data that can help us to develop these applications. And this data doesn't come only from one source, it can come from many different sources. And in this integration of this data is the richness that we are going to generate to create these applications. But there are also challenges when we are working with AI. First of all, the regulatory challenges, how we can access this data. There is also new regulation that is being seen, at least at the European Council, the AI Act that is going to be coming in the coming years. There are also ethical questions like how do we use the AI? Are we creating inequalities when we use them for different applications? There's also the security. Is this AI that we are developing secure? Is it safe? Is it protecting the data? And finally, all the part about what is this data, how do we use it, how do we access it. So today's talk is going to be an intersection between data and the ethical part of the usage of this data. I'm going to be talking about what does it mean to have bias in AI applications, causes, consequences, and the solutions. So regarding what do we mean by biases in AI. So for example, if we look at this example of a model trained to actually diagnose melanoma, in which they use a database that it was Caucasian, so patients that come from with a background that it was very specific, and then you try to check different images to see the progression or the severity of the melanoma. That's going to be fine if you use Caucasian patients, but in the minute that you move into people that doesn't have the same genetic background, then you're going to start seeing that the model that you were using to predict some of this severity of the melanoma is not going to be right, and actually you're going to be misdiagnosing your patients. Another example of this is, we heard a lot about the Human Project Genome, in which we have been sequencing genomes, but it's basically, again, of Caucasian origin, which means that we are actually not understanding, or we are underrepresenting minorities that have not been included in this analysis. For example, African descent, Asian descent, Latino descent, etc. And this means that actually when we are analyzing these genomes to actually understand the causes, for example, for cancer, we might find a mutation that we believe it's perhaps very important, but what it is common for Caucasian background, it might be what is uncommon for Caucasian background, it might be common for an African background, which means that again, if you use this data to create a model to understand the different biomarkers that you're going to find, again, you're going to be causing misdiagnosis, and you are basically creating biases. So at the end of the day, we always have a question to solve a problem, and now we want to use AI to develop it. So we need to actually, to do this, as you all know probably, you need to have data, and we are going to have a training data set of this data that is going to help us create the model, and we actually want to use it, there is an arrow there, in real conditions. And to do this, sometimes we are going to use different data sets that come from different localizations or from different teams. So this is all very good, but sometimes, as I was saying before, the data might come from different populations, so this is the first bias that we might be introducing. Second thing, we might not realize, but most of the time when you create data, it's created in different experimental setups. Most of the public data that we find has not been created the same, so there is already a difference between this, and we need to normalize or to do something to this data so everything fits in one. And sometimes it might be counterintuitive, but sometimes having data that is too clean, that comes from clinical trials, that is very well harmonized, it might be actually not good to create this data, these applications. And finally, sometimes we don't use data that is raw. Sometimes we actually process this data through bioinformatic analysis, and this is what I'm showing here. You might have the same data, but analyzed by two different pipelines might give you very different results, and this processed data, if you use it later, it might actually not be good, again, for your application. So at the end, what we are going to obtain is an application that has a very low performance, either for general usage or for very specific usages. And we need to realize that actually, even if we have many data sets, perhaps they are not going to be good enough because they are too small and it will not fit. So this is another example. For example, this is the same cancer, but the data has been collected from different countries. The data was analyzed with different analytical pipelines, and what you see here is actually a batch effect. What you see is that there are different, the data is clustered in 2 dimensions in very strongly biased by country. So you have France here, you have Canada, you have US, and there is no other difference that you see besides that. So this batch, which is very strong by country, is going to bias your model again. So perhaps the only thing that you're going to be able to predict is from which country this data comes, nothing more. So what can we do actually? Well, first of all, damage control. So first, I think it's very important that we strongly limit the use of the application or the data that we are using. And that we actually avoid, sometimes, perhaps it might be counterintuitive, but perhaps avoid aggregating multiple data sets that are actually going to bring you a batch effect or an effect that is going to be actually hinder the performance of your application. And then we need to face the consequences as fast as possible in thinking that you really need to think what you really want to do, what kind of questions you want to answer, and then actually try to get close to real conditions as soon as possible in a way that you actually find the data that is suitable for the uses that you want to do. As I was showing you before, if we want to do a model that predicts melanoma, perhaps we should include a wide data set with different backgrounds to actually not misdiagnose people. And then also it's quite important to keep entire data sets to actually validate what you have proven before, to make sure that in the same data that you trained, you actually check that it works. Then there are, you can also use other methods to actually standardize your data. So there are classical statistical methods. You can, for example, include batch effects as a feature of your model to try to reduce the effect of the bias. And there are other more traditional methods, combat, SBA, that you can ask our IT team, they will know much better than me, that actually help you actually reduce this batch effect or this cluster effect that you can see. And this is part of what we are doing actually with Professor Blaise Anscar of Laboratory BISC at the Université Paris-Saclay, Université Evry. We are actually using a method which is called domain translation, which originates from computer vision. As you know, most of the AI has been done on vision applications. So it's actually one that is actually going to help us also reduce this batch effect. For example, we have this same location in summer and in winter. At the end of the day, it's the same location. It just changes the moment. So we can actually abstract the same concept to, for example, countries. It's the same data, it comes from different countries, that's it. So it's in a way, a similar way to reducing this batch effect that we might find, actually to try to aggregate data sets. But at the end of the day, I think it's quite important to realize that we need to work with best practices. And the way we see it is in Adlean is that the data needs to be structured at the source. This means at the moment that the data is being generated, many times when we are doing R&D, we actually structure the data at the end of the project when we are just about to publish, and then actually we are losing all the context of the data from the very early on. So what we are producing in Adlean Science is the digital research environment that allows researchers to actually start creating databases using community validated scientific standards. For example, we are working in OSIRIS for cancer and other standards that actually make sure that the data is clean, it's actually well annotated, and actually will be usable later for applications. And not only that, we actually also include all the context, what experiments have been done, what protocols have been used, and the analytics that have been used, the pipelines that we use, to actually make sure that we are able to reproduce the analysis, that we can trace what's being done on the data, then finally help on accessing more diverse data sets that will help us on the development of new AI applications. So that's all I had to say today. Please come to see us in stand number 32 right there on the demo zone, or just stop us if you see us. Thank you very much.